All right, so let's start our lecture today. So this is lecture 3, and today hopefully we can discuss in detail on the subject of full patient influence. So this is our goal today. But before we get into this topic, let's have a quick recap on what we discussed last week. So last week, we discussed, I think, on MLE and MAP. So in MLE, like what we discussed previously on linear regression, we have 3 steps. We always start with 3 steps. So what are these 3 steps? What is the first step? The first step is, anyone? I think you know this. Can you shout and a bit loud, please? Data modeling. So this is a likelihood data modeling. You need to know how to do this. If you do not know, think about this. And if you still cannot find how to do the modeling, you can ask me. Right, so in this case, the easiest one is to start with one data or one sample modeling. So in one sample modeling, because we are talking about likelihood, we always start with probability function. And the probability function here that for one sample is P of Tn given Xn, W, and sigma square. Basically, if you think that it's too complicated, as I mentioned again, start with this one. This one is much simpler. Tn given Yn, and of course there is a correlation between Tn and Yn, as we know that Tn equals to Yn plus some epsilon. And epsilon here is a Gaussian function, epsilon sampled from Gaussian distributions. So because we have epsilon, means that we have a Gaussian distributions that we can sample from, and this distribution has a property, right? And the property is standard deviation, sigma. So that's something that we do not know. So this is, again, in likelihood, is a bit counterintuitive, because the one that is given is actually unknown. Unknown given, right? Unknown given variables. This is counterintuitive because the intuitive one is posterior. Posterior means that, given the known one, we want to know the property of the unknown. But here is the other way around because Tn is actually given. In the training stage, Tn is given. So that is the idea. We want to know the correlation between Tn and Yn. Right? So we can write down this further into P of Tn because Yn is actually a function of xn and w. So we can write xn and w bar, the model, and sigma square. So in the end, we want to model this. Now, as we mentioned here, epsilon is sampled, is drawn from a Gaussian distribution with mean 0 and certain standard deviation sigma square. Right. For that reason, we also know that this becomes Gaussian of the function that is the input, and in this case, the input is, what is the input here? Anyone? What is the input? A function, a probability function has an input, right? Because we want to know what is the probability of that value. So what is the what's the input here? The input is no, Tn is the input. With the mean, you know, you have to imagine this one, because what happened is that you have data, you have an underlying function, and this underlying function is actually your yn or y. In one point, it is yn. So imagine that it's just 1 point, which is yn. So the yn is actually this dot here. You can assume as yn. And xn is this one. That one will be xn. All right. And tn is somewhere along this dashed line. So perhaps tn is there. That's tn. That's for one sample. So for another sample, for example, if you have x, whatever the name there, xi, right? Then you have this one become yi, and ti is somewhere along the dash line, the green dash line. So ti will be somewhere perhaps here. That will be ti. Okay, so that's how you can imagine the correlation between Tn and Yn. And this location, the location here, this location here, that location, the distance between the Tn, the ground truth with noise, and Yn, which is the underlying function, is modeled with that distance. And this distance is actually epsilon. Okay, so the red vertical lines that I just draw is actually epsilon. And as you can see there, so for epsilon n and epsilon I, there is no fixed value. Because when you sample from a random, you sample from a distributions, you can have many different values. Right? So imagine in that space, imagine that you have epsilon here, and this is the probability of epsilon. And the probability of epsilon is really follow a Gaussian function. Depending on your Gaussian function, for example, this one Gaussian function there, right? So if you sample from this, what value that most likely that you will get? What is the likely value of epsilon? Anyone? No yn. There's no yn in this graph. It is 0. It's likely to be 0 here because that's the highest probability. So epsilon is likely to be 0 if you drawn from this distribution of Gaussian function. And large epsilon, this one is large epsilon, or negative in this case, is very rare. But it can happen, but it's very rare. So the same there. So this distance here, the distance of the value of the epsilon, is mostly 0. Mostly will Tn or any Tn is actually likely to be on the red line. But because it's noise can happen randomly, so that can be non-zero as well. And this non-zeroness, actually, if you borrow this Gaussian function here, right, this red Gaussian function, so this is G Gaussian function there, is actually you can imagine in this way. So that's Gaussian function. I put it red color. So that red color, so let's change this red color here. Into green, for example, right? So the red curve here, the red curve that I just draw, this red curve, is actually the same as that red curve. Is that understandable? So you have to imagine in this way. So that means that we want to have Tn, the probability of Tn, given Yn and sigma squared. Again, what we want to know is actually Yn and sigma squared. That's what we want to know. Given Tn, we want to know the Gaussian, because Gaussian here is a probability function. Right? Okay, so that's how we model one sample. And you know that this is a Gaussian function, is a real function. It's one of sigma square root of 2 pi exponential function of minus Yn minus Tn squared divided by sigma squared to sigma squared. So that's the Gaussian function. Right, so after we have this one sample modeling, we have n data sample modeling. In this case, we will write P of T bar given X bar, W bar, sigma squared. So what is the dimensionality of T bar? Anyone? What is the dimensionality of T bar? Sorry? N by 1, that's right. So this one is n by 1, the samples number of the samples. Right? And what is W bar dimensionality? M? Not M, this is a vector, right? M by 1. This is a vector. Vector is always by 1. And X bar is the same as T bar. It is n by 1. Right. So that is the expression for the probability of n data. And this one, we assume that there is independence between samples. So this is a simple assumption that we assume that the different samples do not have any correlation to each other. So in that case, we can assume they are independent variables. For independent variables, that's just a simple product rule. So this one is Gaussian of every Tn given Xn W bar sigma squared. Okay, that's how you do the modeling for n samples. After we know this n samples modeling, the second step is to have the error function. Yeah. Yeah.
You don't change the project after that by doing the log, right?
We don't have the log operation here yet. Everything is still exponential function. Yeah. So this one is still exponential function exactly as this one, Yeah. X bar is n by 1. Well, don't get confused in this case. In this case, I don't really. You are right. I make you confused, perhaps. Previously, we have this notation that Yn is that Yn, yes, Yn equal to sigma in terms of the polynomial function is m equal to 0 until m minus 1 Wm xn power to m, right? And then I mentioned we can use product of factors, dot product or matrix factors operation, basically factor operation to replace the sum, and that one is we can write W transpose X bar, right? So in this case, X bar, Xn bar actually, Xn bar is M by 1 because this one is trying to model that one. Xn is M by 1 and this one is 1 by M. So what is the difference between these two, right? What is the difference now between this one here and that one? This one is simply my expression. You don't need to stick with this one. You can have different notation, of course. But this one in my mind is that X bar is actually X1, X2 until Xn. While this one, Xn bar, is actually Xn power to 0, Xn power to 1 until Xn power to M minus 1. Okay, so there are two X bar there. One is X bar to represent the samples, and the other one is Xn bar. Xn bar is when you do the multiplication or do the modeling with respect to the polynomial function. So please don't get confused here. All right? Any questions? Any other questions? Okay. Right, so that's a bit of the definition of X bar. So after we know X bar here, what is the error function that we want to have? Well, the error function is very long, so I don't want to get into all the derivation. So basically, we want to have W bar sigma square optimum, both of them. And this one is try to maximize argument max with respect to W and with respect to sigma square on the whole data and data. So maximizing this, in the end of the day, you will do the minimization of mean W sigma square, and then this will be very long here. So it's over n, sum over n log square root of 2 pi plus sum over n 1 over 2 log sigma square plus sum over n W transpose Xn bar minus Tn square there divided by 2 sigma square. Well, you can look at the lecture notes for the definition for that one, right? And that's become our error function. So basically the error function is this one here. This the whole things become error function, which is E. E of W bar and sigma square. So that one gives you the definition of your error function. Any questions here? Yeah.
I have a question about this one from the last time lecture. So what you did is that you changed the product, right, by the sigma log. So you took you changed, right? You took the log of both sides.
The product sign becomes the sum operation.
And
yes.
So how did you change from the product sign to the log, to the sum of the log?
Yeah. So basically, log of a product of X I here, for example, equals to sum over I log Xi. So that's the basic thing.
So you took the log of both sides to reach this one, right?
I put the log in the both sides, yes.
But you didn't change the left side. Still the same.
That's right. So as I mentioned again, you have to know about the argmeans operation. So when we have A star equal to argmean, in this case A, right? And then you have product of I, AI, for example, right? So log, what you have in mind here is that assume that the I is a function Let me see. So assume that I is any function, something like that. So this one is a function of the product, right? And in the end of the day, we know this one is A star. That equation is A star, right? And then you do the log operation. So I do not know what is log operation, but it's, I know that it's proportional. So when the red line is going down, the log is also going down. Means that whatever that log gives you, it will be going down because the original line is going down. When the line is going up, I know that the log of that function is also going up. So I get that one. So this one may be different. In the y-axis is different, but in the x-axis doesn't change. So that's why it's called argmin. So if you just take mean, of course the mean is different, but its argmin will be the same because argmin is the x-axis. But mean alone without arguments, it will be the y-axis. So again, for those who don't really much understand that, if I remove the arc, right, and I have B, for example, there, so that one gives you this one, B. If I put log here, log B, for example, of course it will be smaller in this case, but in our drawing here, let's assume that's become bigger, right? So that one is log B. Okay, so that's if you don't use arc. Any other questions? No questions here? All right, good. Yeah, please ask this kind of question because I do not know that you do not know. So that's something that's difficult to guess. What is the level of your knowledge? But anyway, so again, if you don't understand, please ask. Now, we know that after we do the second step, the next step will be optimization. So the next step is optimization, in this case, minimization. And in the end of the day, we have to minimize dE of W sigma square with respect to dW, and also dE W bar sigma square with respect to d sigma square, and both of them equal to 0 because that is quadratic function that we are dealing with. Right? Now, we know that if we do this operation with respect to W bar, we will end up with W bar equals to X plus T bar. Okay. Any questions here? Then we know that it's exactly the same as least squares. And then for sigma square, we end up with an equation sigma square equals to 1 over n sum over n W transpose xn minus dn squared, which look nice because we can have sigma square, and sigma square is important, right? Why sigma square is important to get? Why sigma square matters here? It gives you the uncertainty value. Why that give you the uncertainty value? Because we use Gaussian function. Here, remember that sigma square is Gaussian function parameters, right? So Gaussian function parameters is something like this. This is, what is the x-axis? What is the x-axis? Anyone? What is the x-axis? Well, close to epsilon, but it's not epsilon actually. It is the probability of, well, you can look here. Let me see. This probability that in the green box there. The probability of given Vn, what is the accuracy of Yn? So if Yn and Vn is very close, 0, for example, regardless of your sigma, it will be the highest, right? That's the Gaussian. So the Gaussian, because the mean is here, the mean is yn. Look at this again, this equation here, that equation. Yn is the mean. So if you imagine this equation, yn is there, the mean of your Gaussian function, right? And the peak here is when yn equals to Tn. So when yn equals to Tn, you will get that highest probability. When Tn is far away from Tn or yn, or again, if Tn is far away from your yn, the probability will be much lower. Now, if you have two types of probability here, right? One is with sigma very small, and the other is your sigma is very large. Your sigma is very large, something like that. Okay. So which one is more certain? If you have, I mean, more certain here, higher probability. Of course, the red one is higher, right? Obviously, from what I draw, but actually, even if you do the proper drawing of Gaussian function, when sigma is small, it's always higher than when sigma is smaller. Even though yn and Tn is the same, there are two things here. Yn and Tn for the red line, for the red curve, and yn equal to Tn for the green curve. Regardless whether Tn and equals to yn or not, the red one gives you higher probability than the green one. And what is the difference here? The difference here is on the standard deviation. So the standard deviation here gives you the indication of your probability. Does it make sense? All right. Okay, so that's why sigma is important. Right, so now we're happy with this. It seems that we're happy with this, right? We have the sigma, and we can compute the sigma after we know W. So in this case, the sigma indicating the W, how good is your W? It's the same thing like how good is your Yn? Because you cannot know about Tn, right? Tn is something already given to you. It's the data. So the probability here is talking how confident are you with your estimated W. That's the meaning of sigma here. Again, the meaning of sigma is how confident you are with your estimated W. Because in the end of the day, this is the output, the predicted parameters. Right? And if you know W, you will get sigma. In this equation, if you know W, you get sigma because everything else are known. All these are known. The green one are all known. Seems like a good news for us, right? Because knowing W, you know the uncertainty, you know the probability of that W. But the problem here, as I mentioned again, this equation, that equation here, depends on M. If your M is very high, then this one here, the subtraction here will be very small. Because if M is very large, then however complex your Tn, your curve will be able to predict that precisely. And if it is 0 all the time, because M is very large, means that Yn is always the same as Tn and give you 0, means that sigma square will be small. Right? If it is 0 there, sigma will be 0 as well. Means very, very confident. And that's the problem, because we do not know M. We can set M as much as, whatever value that we like, right? As large as possible. So that means that we cannot trust sigma square because that depends on our setting. So that means that sigma square in MLE is useless, meaningless. And if sigma square is meaningless, then we only end up with this prediction of W, which depends on M. And it is exactly the same as least squares. So that's why people say that MLE is actually the same as least squares. Any questions here? Right? Okay, so because there is still a problem and we don't have any progress, then we have to think about other types of inference. And the other types of inference is MAP. So in MAP, we also have 3 steps. The first is posterior data modeling. So in this posterior data modeling, we know that posterior definition is P of what? Let's look again. We have variables, right? So variables is always Tn followed by Xn. This is really the input. One is the label and the other is the known variables Xn. And this is again the input. It means that they are known. And what is the output that we expect? What is the output? What is the output that we want to have all the time? W bar. That's right. And we know that the modeling of Xn and W bar, which is Yn, where Tn is a Gaussian. The error can be sampled from the Gaussian function. So that's why we have sigma square. And these two are unknown. That's something that we want to know actually. So the unknown here is the output. Okay, so we have input, we have output in these variables. Now, when we talk about posterior, if we talk about posterior, we have to define P of what? Unknown or known? Unknown. That's posterior is something intuitive because given the unknown, we want to know the unknown given the knowns. So this is basically a posterior. So this is the basic idea of posterior, which is different from likelihood, because likelihood will be P of knowns given unknowns. So this is very basic and you have to know the difference between posterior and likelihood. Okay. Okay, so because we are dealing with posterior, we have to define P of unknowns. And P of unknowns here is W bar and sigma square. Okay. And the knowns one is actually Tn given Xn. Now we know that in our modeling, so the modeling, we use Yn to represent the output that have to be the same. This one has to be the same as much as possible to Tn. And Yn is the representation of the curve, the red curve, underlying the data that we want to find, the line fitting. And this one we know that this is a function of W bar and Xn. Right? So because Xn is always known, we don't really bother about Xn. What we want to know is again is W bar, right? So W bar, when we talk about W bar, it's actually we imply Yn. So Yn and W bar is like a twins. Okay, so they are interchangeable from each other because Xn is known. All right, so in that case, we can write, because of this reason, we can write the P of Yn sigma square, if you want, given the n. That becomes our posterior. So this one is again posterior. Does it make sense? Any questions up to this point? Okay, so in that case, we can just use Bayes rule, right? So if you use Bayes rule, first of all, you can write Tn or Yn sigma square. This is joint probability of all variables divided by the given one. The given one is Tn. Okay, and we know that this one is again is posterior. The left side is posterior. According to Bayes, we need to form what? If we want to know the definition of posterior, then we have to form the likelihood and prior. So that is really the basic thing, right? If you use Bayesian, you have to use likelihood and prior. So we have to form likelihood here. So how we can write likelihood? What is the likelihood definition? It's knowns given unknowns. What is known here? The n given Yn and sigma square. Right? If we do this, means that this one have to kick out. Have to be kicked out from this parenthesis, from this bracket. So in that case, we have Yn sigma square because they are kicked out. Basically, this kick out here means that I just want to make the explanation easier, but this is actually product rule. This is the definition of product rule, right? And divided by P of the n. Any questions so far for this derivation? So you have to be fluent on this, because if you are not fluent, you will get lost and you cannot do the derivation by yourself. Again, this is a product rule. Now, the problem here, we know this one already, right? We don't really have any problem with the blue one, because we already know the definition there in MLE, in the previous discussion. The unknown one is the second term, which is the prior. The prior here is something that we do not know. It is a new term for us. Well, we know the last one is evidence. The evidence here is this one, the yellow one. We know that evidence can be cancelled out anyway, so we don't really bother about evidence for MAP. Okay, so the most important one in our discussion is the red one, the prior. Okay, so let's look at that. So this one then equals to P of Tn. I just removed the evidence. So this one is proportional, right? Ptn given Yn sigma square. Now, to make our life easier, we assume that Yn, your curve, is independent from noise. Noise here is sigma square. Okay, so regardless the noise, it doesn't influence, doesn't have any direct correlation with your prediction, Yn. So in that case, we just split them because they are independent from each other. Is that correct? Yeah, it's correct. Now, this one equals to P of Tn given Yn. I put the definition of Yn. Yn is actually the multiplication of W bar with Xn, right? Sigma square. And I can put P of W bar Xn P of sigma square. Correct? So now let's assume that we do not know, we don't have any information for this. That's the problem with MAP. you have to, if you want to use efficiently, effectively, then you have to know all this prior definition. In many cases, you do not know, you don't have the information for that particular variables. Of course, if you can, if you have to use that because that will be very useful. But if you cannot to find any prior information, what you do then, if you cannot find any prior information? Assume to be. So when I talk about prior, right? So for example, in this case, sigma square, if you know prior, the prior sigma square, you will put more focus, more attention to a certain value. For example, you know that 0 here is likely the value of sigma square, for example. So then you can use a Gaussian function to model that. This case, it means that 0, sigma square equal to 0 will get more priority. We encourage sigma square to be 0. That's the meaning of this. But if you do not know the preference for the values of sigma square, then what do we do? What kind of line that I have to draw if you don't have the preference? It is what line that I have to draw? Yes, horizontal, exactly. Because if you don't have any preference, what you need to do is just to be uniform. So this is uniform distributions for all the values of sigma square. If it is uniform distributions, what does it mean by this? It means that probability of sigma square is, yes, it's flat. It's flat means constant. The probability becomes constant. You can replace this constant value using C, for example. Right? But in the end of the day, the exact absolute value of C doesn't really matter because we use maximum, minimum in the end. Right? And it is proportional anyway in the end. It doesn't really matter what is the absolute value. So because it's constant absolute value and we don't need to have the absolute value, then we can just assume this is equals to 1. And if that equals to 1, what does it mean? We can remove it out. We can remove this out. Okay? Right. So now we have a simplified version of this, which is this one, right? And then let's do further derivation. P of Tn given W bar Xn sigma square. Again, if you know the correlation between Xn, your data, and W, which is your function of the curve, you have to find the function. But if you do not know, then you can split them, assuming they are independent from each other. So this is the techniques in data modeling. This is really up to you, whether you want to have a complex function or you want to have a simple function, and so on. Of course, if it is too simple, then it will not be precise in estimating your value. Okay? But for the sake of learning today, let's have some simple example first. So this is a simple example we can split between W and Xn. They are independent. Now, Xn, we have to find some function. So what is the probability of your Xn? Xn is the year of the price. The probability of this year and the probability of the next year, the probability of the next year after that. So it seems to us there is nothing that we can define as a function for this year, right? The time is flat. Time seems to be uniform. There is no private time in this time domain. So we can assume this is also flat, uniform for all the times. So we can remove this. Well, actually not remove, but we assume that it's constant and it's equal to 1, and it doesn't really matter what the value there. In the end of the day, that's something that we end up with. Well, if you assume that P of W equals to 1 or uniform, then you can, reverse to MLE. the MAP here will be useless. So we should not, for the sake of learning MAP, to define P of W equals to 0 equals to 1. We have to do something there. We have to define it. We have to find function to define P of W. So now the question is what kind of function that we can define. So what function here, right? This is a big question in MAP. And in MAP is always like, what is your prior function? What is your prior knowledge on W? Again, what we learn to answer this question, we also learn that this one is actually likelihood. In likelihood, we know that sigma, we encourage sigma to be, in likelihood there are two parameters, right? W bar and sigma in learning MLE in likelihood. And in likelihood, we encourage sigma to be equals to, we will be happy if sigma equals to 0. We're happy if sigma equal to 0. And to make a sigma squared equal to 0, what do we do? Sorry? Yeah, so in that case, what kind of setting that we need to do? Increase the values of which parameters? M, the complexity of the model, the magic number for your model, right? So in this case, this implies the likelihood encourage sigma square as small as possible, if possible equal to 0. The implication of that that kind of action is to set M equals to as much as possible, as large as possible. So we encourage M, the likelihood, not us, but likelihood encourage us to set M as high as possible. That from the perspective of likelihood. And what is the effect of this? What is the effect of large M? Well, the effect is sigma squared equal to 0, right? But what is something to do with us here? It's over fitting. So this one, M large, is also implied overfitting. And we don't like this. And this is the problem with MLE. And this function here for the prior should be able to handle this. Well, M is large is something that we have to accept. But overfitting is something that we don't want to accept. Okay, so M can be high, but if it doesn't overfit, it's good, right? Doesn't really matter to us. So now P of W here, the prior, have to overcome this overfitting problem, even though M is large. So how? Again, M is large means that your function of your N equals to W0 xn0 plus W1 xn1 plus W2 xn2 plus Wm xn up to M. That means that M is large. And this one makes the line overfit to your data. It's very, very overfit. So what do we do then? We cannot prevent M to be large. So this one has to be capped. You have to keep M large because that's what the likelihood want. Now, what is the prior can do? To cancel some of them, exactly. So to cancel as many as possible term. So how we can cancel this term? To make Wm equals to 0. We encourage Wm equals to 0. So again, the encouragement here, we can use Gaussian function to encourage. Means that we can use P of W equals to Gaussian function given the input of W with mean of 0, because the mean is something, if we encourage the mean equal to 0, means that most likely the W will be equal to 0. And we have alpha as the parameters, hyperparameters, and the identity matrix. Why we have identity matrix? Because this one W is M by 1. It's not a scalar anymore. It is multivariate Gaussian. So this is what we call multivariate Gaussian, multivariate or multivariable Gaussian. Because we don't have M here is not equal to 1. M can equal to 100, 1000, and so on. So it's very huge in terms of dimensionality. And in multivariate Gaussian, the equation is different from this one. You cannot use this equation anymore. The green equation. This is a single variable. So this is univariate Gaussian function. So this one is univariate Gaussian function. Okay, but the meaning is the same. Only the dimensionality are different. Right. So because it's multivariate Gaussian, here we don't use a standard deviation anymore, but we use, what is the term? We don't use standard deviation in multivariate Gaussian. What do we use then? What is the name of this? It is called? It's called what? Covariance matrix. Covariance matrix. So it's matrix, and this is covariance matrix is always square. Okay, and symmetric actually. But anyway, so this one is M by M. So if your M is large, then the matrix will be very large. But that's how we model the prior. So you know the meaning of this equation now, right? The meaning is that we encourage W to be 0 because the mean of this Gaussian function is 0. Any questions so far? Okay, so as you can see here, there is a battle between likelihood and prior. There's always the case that these two terms will try to battle to win from each other. Okay? The likelihood want to have M as large as possible and the error to be as small as possible, but the prior want you to be underperformed. Okay, so the prior wants you to be underperformed, underfitting, but the likelihood wants you to be overfitting. And because they battle from each other, to each other, and if you optimize them, then you will have the optimum value between these two terms. Okay, so that's the meaning of the first step, which is posterior data modeling. So in the end, we have posterior P of W bar xn bar, xn sigma square given Tn, or you can simplify this into P of Yn sigma square of Tn equals to P of Tn given Yn sigma square P of W bar. Okay, so that's your by the way, this is proportional. Then this one is a Gaussian function. The likelihood is Gaussian function of Tn with mean of Yn and sigma square. And this one is probability of Gaussian function of W bar with mean of 0 of I. So that's your modeling. Okay, both of them are Gaussian function. Any questions here? If you don't understand, please ask, because if not, you will get lost all along the way. Again, if you don't understand, please ask. Okay, so then the second step, again, this is only for one sample. You can extrapolate this into n samples. So for n samples, P of y bar t bar equals to, I simplify a lot here. I don't really write all of the variables. Again, for simplicity, let's assume we just assume from one sample to the other samples, there's no connection, there's no link. Okay, of course, in reality, there should be some link, but let's assume that for simplicity, they are independent. So in that case, we can just write down in this way. Right, any questions so far? So if there's no question, the next step is error function. So the error function is to maximize the posterior, basically. So in this case, we want to maximize, we want to have W, and of course sigma square, but I just remove sigma square in this case. Rmax of W bar P of y bar t bar. Again, this one refers to that one. So I will not do the derivation here because it's very long. It's very long. So, and in the end of the day, this one is arc max of minus n divided by 2 log 2 pi plus n divided by 2 log beta. So what is beta here? Beta inverse is actually sigma square. It's called precision. So if sigma square is called standard deviation, beta is called precision. Right, and minus beta divided by 2 sum over n W transpose xn minus tn square minus m divided by 2 log 2 pi. Yeah, it's very long. But if you want to know the full derivation, you can look at the lecture note. Plus m divided by 2 log alpha minus alpha divided by 2 W transpose W. Okay, so that's the whole things here. The whole things here is your EW. And that's something that you have to maximize. And if you want to minimize of W, then you can just put minus there. Okay? Any questions here? Oh, by the way, you have to understand this anyway. If you don't understand now, I will force you, unfortunately, to understand this by putting this in your assignment. So you have to implement this in your code. Okay? So you will implement this. Well, not this equation, of course, but the end product of this. You have to do the implementation. And in the final exam, of course, the question will be taken from the theory side. Anyway, so again, any questions here so far? Okay, so if there's no questions, that's your E. So the third step is optimization. In the optimization, the simplest way is that dE dW equal to 0. So here, if you, with respect to W, right? If it is with respect to W, you can just forget about that one. There's no W there, so it's constant. No W there, it's constant. There is a W in the third one. The fourth one, there's no W. This one, there's no W. So actually, you end up with optimizing to terms. Okay, so let's try to find the derivative of that two terms. So in that case, for the first term, so the first term here, I mean, let's put it in different color. So this first term in the red, right? If you do the derivative of on this one, 2 to the power 2 will go down and cancel with 1/2. So you end up with beta. You end up with beta there. And because there is minus here, you see that minus here, right? But you also minus there, they become positive. And sum is, when you do the derivative over sum, is still sum. And the function under the square root, under the square will be just of this own function, right? And then you have the derivative on something inside the bracket. Okay, so something inside the bracket, Tn is constant, so you don't really care about Tn. And then what is the derivative of this term then? Is xn, right? So that's it. That's for the first term. The second term is also have minus there. The second terms here, the green one or the blue one here. The blue one has a negative, and we have negative here as well. So they are cancelled, right? They become positive, so we can plus here. So what is the derivative of alpha divided by 2? Alpha over 2 with respect to W transpose W is still alpha divided by 2. Well, W transpose W bar dW bar equals to what? 2 W bar. Anyone confused with this? W transpose W equals to what actually in scalar? It's W squared. It's the same as W squared. So that's why this becomes 2W. So here become 2W bar. And then you cancel the 2 here. Okay. Any questions? So this one, you have to learn about multivariable calculus. Multivariable calculus. Any question, anyone? Okay, so and then it has to equals to 0. Now, this one, we learned about this before actually. This one, the green terms there, we learned about this when we do, actually we did it twice. One in the least squares discussion and the other in the likelihood MLE discussion. So I don't want to repeat here. In the end of the day, if you look at the lecture note, you will see that it becomes X transpose beta multiplied by X transpose X W bar minus X transpose Tn or T bar plus alpha W bar equals to 0. Okay, so you have to transform the sum. Again, we don't like sum because sum is troublesome. Okay. So we transform the sum into matrix operation. Right. So we're almost there. So in the end of the day, we want to find this W. So we want to merge them, merge W into one place. Before merging them, oh, this one is a beta here as well. There's a beta term there. So in this case, beta is troublesome. So we move beta. So we move beta, and everything is divided by beta there. So 0 divided by beta is 0 anyway, right? So we don't care on the right side. Okay, so based on this, we can have X transpose X plus alpha divided by beta W bar. Agree with me? Because we want to merge the terms with, that have W bar equals to what? Equals to X transpose T bar. Again, then from this, we want to know W bar. So W bar equals to X transpose X plus alpha beta. You need to have I here actually. This one has to be I. But anyway, so don't bother about this. I will explain later. Inverse X transpose T bar. So this is the most important equation that we have. And this is the equation that you have to implement in your code. It's very simple in the end, right? But you have to know about the matrix formation. If you're not careful with the matrix formation of X there, your code will be wrong. Okay. Right, so now let's check the dimensionality first. What is the dimension of W bar? M by, so everything here on the right have to be M by 1. So what is X transpose? Anyone remember? So T bar is N by 1, right? So here X transpose should end up with N by M. So this one we know M by N, and this one is N by M. So in the end, it is M by M. Here, the identity matrix have to be M by M, right? So that's correct. In the end, we have M by M. You can inverse this one, M by M matrix, right? Because they are square. Because they're square, you can do the inverse. And the output of this inverse will be M by M. So in the end, everything in the bracket will be M by M, multiplied by M by N, and then N by 1. In the end, is give you M by 1. Do you see any difference between the solution of MAP and MLE? Do you see that? Yes, the difference is only in this term here. Only simple kind of additional term. But the effect is very huge because with that term, you will no longer have any overfitting problem. It looks like simple, right? But to get here in the beginning, you have to think what kind of W that you have to find as a prior. And if you find that modeling in the first place, the derivation up to this point here will be mechanical. You can just follow the normal mathematical derivation. So the most important things that you stuck, it's likely that people stuck, is when you do data modeling. So be careful with data modeling. Either the likelihood or the prior. The data modeling is never easy. But once you have data modeling and your data modeling is correct, the rest is just mechanical. Any questions here, anyone? Yeah, again, you have to implement this. So this is your first assignment to implement MEP. The good thing is that I will give you the exercise, like last week, I give you the exercise as well, right? With the, questions and answers. So you can learn from that. So the same in the exercise 2, I will give out the code for MLE. Okay, so you can look at the code for MLE, and then the MAP will be quite straightforward, I think. But that's the first part of the assignment. So the assignment is likely to have 5 parts. Okay, so I will release this part one by one. So this week I will release 1 part for MAP and perhaps full Bayesian to some extent, or basis function to some extent. But anyway, so any questions so far?
One question about the homework.
Yeah.
You said that would be 5 parts and to release.
It's likely to be 5 parts. It's not yet certain, but it's likely the plan is 5 parts, yes.
How many weeks are going to release them?
So I try to keep with the lectures. So once I finish the lectures, then I will release the assignment or the parts until the end of the first part. So the submission will be recess 1 week after recess week. Because the first week of after the recess week, you will not have any assignment from the second part. It's likely from the second part, the assignment will be released in the 2nd week or the 3rd week. Okay. Does it make sense? Okay. Any other questions? Right. So if there is no question, I will give you an example, some example, or some intuition behind the code. Okay, as you can see here, I'm using Jupyter Notebook. So this is Jupyter Notebook, and let's see if I use MLE, right? So this is the one that I will give to you, not in terms of the code actually, but I will screenshot and give you the screenshot. Means that you have to type yourself, right? You cannot copy and paste. Because if you copy and paste, you will not learn anything. Okay, so anyway, so this is the code. And right, so this is MLE. This one is M equal to 30. So let's assume the underlying, let's look at this one by one first. This is not the main is here. So first is we generate true data. So this one is the true data, the actual distributions. And then we fit on the actual data. Means that we will have, in this case, the red line. So the red dots are the actual data. And the red line is the line fitting on the actual data without noise. And then we add noise to the true data. So the green one is actually the noisy data. And the green one, the green samples here, or the green dots, are your input. Okay, so your input is not the red dots, your inputs are the green dots. And from green dots, you try to find the red line. Okay, so that's the task. Given the green dots, your task is to find the red line. And in this case, we estimate the curve using MLE. And M, for example, and we do not know what M, so let's assume that M equal to 0. M equal to 0 means that it's a straight line, right? Horizontal line. And that's what you get, which is exactly in the middle of the data. And we increase m, for example, m equals to 2. 2 means that it will be a straight line in something like that. And this one is not really straight line actually. This is a quadratic function with one inflection, but it's not really shown here. The inflection point is not shown here because the inflection point is somewhere here. So it's not shown. It's not a straight line, but it's a curved line. Let's assume there's 3. 3 seems to be correct, right? Because there's 2 inflection points. And 2 inflection points is actually cubic, right? And we have cubic is actually m equal to 3. And that's the blue one is your estimation. The red one is the correct one, the ground truth. This also seems to work if we know m. But unfortunately, we do not know m. So in that case, we overshoot m, for example, 10, and see what happened with 10. And that's what you get. It becomes somehow overfit. Right? It's too complex compared to the real one. The real one is only 2 inflection, but now you have many, many inflection points. Right? So that's the problem of MLE. Okay, so this is the problem of MLE. And I can tell you another problem. It's not just MLE in this case, in a practical sense. In pen and paper is fine. The polynomial function, I mean, is fine in the paper and pen. But in programming, there's a problem with polynomial function. Why? Because when I set it is 150, for example, right? 150 means that it's very, very complex. The power is up to 150. For every data, this power to 150. It's a very huge number. And that creates a numerical problem. So what's kind of numerical problem that you have? You will end up with something like that. It's not flexible because it's too huge, the power. So that's the problem with polynomial function. When you have m so large, means that the power to that large number will be very large. Or in some cases, because if it's fraction, it becomes very, very small. So there is some numerical problem with polynomial function. And that's why we have to use basis function. We will soon discuss about basis function. But if you use basis function, this one is the code for basis function. So this is the code of basis function. I also set here m equal 150, and alpha is almost 0. Means alpha is the prior terms. So if alpha is very small, means that if alpha equal to 0, means that I don't use the prior. I just use MLE basically. But unfortunately, in this case, I cannot set alpha equal to 0. I just put alpha equal to very, very small number, right? But it's the same thing, the same as alpha equal to 0. So if you use basis function, it is more stable. So this is something that we expect when it is overfitting. Okay. So we will soon learn about this basis function, and your part of the assignment is really that you have to use basis function. Anyway, so that's the point of polynomial function versus basis function. The other point is this MLE versus MAP. If it is 0 here, it is MLE. So if I have that one and 150, for example, 150, and then I execute this one, well, it's the same. It's a numerical problem there, right? But if I set alpha, although I set m is very, very high, but now I use a certain value of alpha, 0.01, for example, and that's what you get. It doesn't overfit your data. It's very different from the previous one, right? The previous one, well, I show you MLE here. This is MLE. Of course, if it is high, you cannot see because the problem with numerical values. If it is 50, not 50, maybe 30 or 20, well, there is a problem with overfitting here, right? There's too many inflections. So let's see if it is 60, what happened then? So basically, this is overfit here. Although the rest is not really, there's instability of the numerical, you see that there is a problem, there is overfitting problem. Right? So the same setting, I put 60 now, or even 150, or 60 if you want. But alpha now, I enforce alpha in certain, for example, 0.1, right? So I enforce some alpha there. So that's what you get. It is regularized. It's not overfit anymore. Does it make sense? So this is the power of the prior MAP. Although you do not know M, you set M as high as possible, but the regulator, the prior in this case, can that kind of effect. Right? It's trying to make the curve to be not complex, to be underperformed. Anyway, any questions here? Any questions, anyone? All right, so yeah, so this is something that for the assignment. All right. So that's all actually for MAP. Before I continue, any questions for MAP? Any question, anyone? No? So remember in MLE, we discussed a bit about sigma square, right? We just give you the power of knowing the uncertainty or probability. So now in MAP, where is sigma square? Where is there? Is there any sigma square? Yes, there is sigma square, but again, the sigma square there is meaningless as well. Why it is meaningless? Again, the sigma square will be similar to, you can compute yourself for sigma square, but it's similar to MLE, but that's not the problem. The problem is that in MLE, by definition, when we have posterior of Pyn or Pw bar xn given Tn, right? That is a sigma square, so you can have a sigma square there. In the end, this one is proportional to P of Tn given W bar xn sigma square of Pw bar. Now, the thing is that in MAP, so MAP here, this term gives you sigma. This gives you sigma square. And the sigma square only for this term. Only. There is no sigma square for the prior. The prior is independent from your sigma square. Even though you know sigma square, you cannot know the probability of this posterior. Why? Why can you cannot get the sigma square for that posterior? Because it is not equal. This one is not equal, but it is just proportional. So the value that for this multiplication, the value of this multiplication of the probability is not equal to your posterior probability. This is your posterior probability, right? And this one is the multiplication of your likelihood probability and your prior probability. The multiplication of these two doesn't give you the probability of the posterior because they're just proportional. If you want to know the probability of the posterior, what do you have to do? If you have to, remember in the beginning of discussion, you have to normalize this. Yeah, normalize this with P of Tn. You have to normalize. If you want to make this equals, you have to normalize with P of the n. The problem is that we do not know P of the n. And in MAP, we don't care anyway about that. So by nature, MAP doesn't give you uncertainty because it doesn't give you probability. The output of this multiplication is not equals to the posterior, it's just proportional. So for that reason, MAP by nature, by definition, doesn't give you any uncertainty information. Does it make sense? Any questions on this? Yeah. So that's what we want to pursue further. Actually, this is something that we want to pursue further. This one. We want to know the probability of the posterior. If we can have this one, that's the goal. If we can reach this one, we don't want to have this course anymore. We stop there, right? So if we can have this by the end of this lecture today, then there will be no session next week. Because that's the end of the goal. We want to know the posterior probability. And this is the goal of this first part of this course. We want to know the probability of the PW bar. Okay, any questions here? And this one will require you to learn about full Bayesian. Okay. Any questions here? I will explain later on why we don't stop on the full Bayesian, but let's postpone that discussion later on. Any question, anyone? Okay, so before we get into full Bayesian inference, let's discuss first on basis function. Okay, so let's learn about the concept of basis function. Oh, by the way, let's have a break because the time is just fine for having a break. So let's have a break for 15 minutes. So we start again at 7:45. Let's have a break, everyone. Yes.
I have a little bit problem with this part. Like from here, we are doing the W transpose xn times xn.
Yeah.
And then you come with.
Yeah, there is a step there in the lecture note that you have to follow. There's not many, but 2 or 3 steps in between.
Yeah, I'm just asking why this one can be common to this, because this one is a 1 times m, but this one is a n times m.
Which one is that?
Like the transpose of W is 1 times m.
Yeah. So this one for the explanation, actually you should look at lecture note number 1. You look at the lecture note number 1. Lecture note 1 when we discuss about least square. Not number 1.
I don't remember.
Yeah, so lecture number 1. So this one, do you have this introduction?
Yes.
Right in the end. So here, so this one, right? This is your question. From this one, how we can get this one, right?
Yes.
So see the additional node.
Let me.
So the additional node is here. So this is the whole explanation on that.
Okay.
Yeah. Yeah.
Why is
so we assume. Just assume. Maybe they're not independent, but we assume in this discussion to be independent.
I just wonder, how is the alpha defined?
Alpha is well, it is multiple dimensionality, but I just simplify into 2 dimensions. That's alpha. So this one is W. This is property of W.
So the identity matrix.
So why is identity matrix? Because it's a multivariate Gaussian. Multivariate Gaussian is multiple dimensionality. For example, this is W1, W2. This is a property of W1 and W2. And then this one is a 2-dimensionality. Okay. So now what is standard deviation here? So you have 2-dimensionality there, right?
Yes.
So we assume that they are the same. So alpha here. But then you have to become a covariance matrix. So alpha I is actually the covariance matrix, Gaussian of W bar 0. This one is actually covariance, right? And this covariance is actually a matrix. So for example, this is 2 by 2. 2 by 1. This is 2 by 2. 2 by 1 is W1, W2, right?
Yes.
So this one become alpha, 0, 0 alpha. Identity matrix, you know identity matrix, right?
Oh, yes.
Yeah, so this one is 1, 1. So that's why it's multiplied by alpha, alpha. So this one is alpha, alpha here. 2 dimension.
So there's no relationship between different curves.
No, we assume that it's independent.
So
yeah.
Thank you for that. So Unicode change from 10 to 100 or 1,000.
No, I do not know. That one is up to you to define.
Yes, I know. But here is one divided by.
Sorry. One is yeah. Sometimes I use inverse. Sometimes I don't use inverse.
So
I think it's, the correct one is should be inverse. Yeah.
Sorry, I didn't catch this part. Why do you say actually we can't have any uncertain information about?
Because the definition of a MAP, right? MAP is P yn given Pn. Right?
Yes.
It's actually equals to Pn given by yn Pyn divided by P of the n. But this one is difficult to obtain. So that's why in the MAP is independent anyway from W.
Yeah.
So this constant, right?
Yes.
For respect to W.
Yes.
So this is proportional to Pn Yn.
So I would say we can't.
Pyn.
Uncertainty information is about this sigma square, right?
Yeah, but sigma square with respect to this probability. We want to know the probability of this. Probability of this function, not probability of this multiplication of this.
Yeah.
We know the probability of the multiplication of the first probability. We know this one. We know this one. We can know this one.
Yeah.
But the multiplication of this doesn't mean property of this.
Then how come for this W we can actually get?
Yeah, because only W we can get, but we do not know the probability of W because we maximize this. So there's an argument max, right? Argument max with respect to W. So argument max is only give you W, doesn't give you the probability.
I see. Okay, thank you.
Yeah.
I just want to go through the lecture one more. That one only talks about if A multiplied by A, then is A transpose times A.
Oh no.
Huh? Is it? Then that one is not inside the lecture.
No, this is lecture additional note. This I print from the lecture note.
Yeah, this one talking about you see the. These two
So
are
this one, right?
identical.
This is your problem. How can we from here to here?
Oh no, that's not my question.
Oh, so you know this one?
I know this one.
Okay.
No, but I mean, when there are like three things together, I'm confused why this one the order is like x and t then x and.
Oh, that one. Oh, okay. So YW transpose W transpose X and
yes.
bar multiplied by
xn. Yes.
Right, bar. This one, you have to look at the dimensionality. What is this 1 by m, right? This is m by 1.
Xn is n by m.
This is m by 1, right?
This two are different. This x is different from this.
Yeah. But this one, I'm just following you. This one is not matrix, right? This is vector. W is a vector, right?
W is 1 by m.
1 by m.
Yeah.
This one has to be m by 1, right?
Oh, so this one, just one is, so this one is different from the x.
This is matrix.
Oh, this is the.
This x in this case is matrix. This one is the vector.
Oh, I think that's where I get confused. So this one is actually
a vector. Everything is a vector.
This one is m by 1.
Yeah, and this one is also m by 1. If you do this operation, it doesn't really make sense, right?
Yeah.
Well, it makes sense because it is 1 by 1. It's okay. Scalar multiplied by a vector is okay, right?
Yeah.
A multiplied by x1, x2 is okay, right?
Yeah,
yeah. So actually, it's okay. We can operate in that way, but there's a more elegant way to do it by having this multiplication to be able to be operated first. Because it doesn't matter, multiplication, you can multiply this one and then multiply that one, or multiply this one first and multiply by that one, right? So if I want to do this first, I cannot do that because m by 1 multiplied by m by 1 doesn't really make sense. So in that case, I can transform this into xn transpose xn, right?
Yes, correct.
In this case, it will be 1 by m by 1.
That's 1 by 1.
That is just in the end, 1 by 1. And you can have W bar in this case. You don't need the transpose. It's the same, right? Identical. This is m by 1.
But this one is 1 by 1, 1 by 1. So this one is m by 1.
Yeah. So the same, right? This is 1 by 1.
Oh.
This is m by 1. It's okay, right? It's the same, right?
Huh? Is it so? Oh, so both are m by 1. Oh, then this one is.
That's matrix. That's matrix that you have to understand how from vectors into matrix.
So it's the same.
Yeah.
Oh.
Yeah.
Okay.
No. Yes.
I have a question about the code assignment.
Yeah.
Do we have to install any software or finish some
Python? Python. Jupyter Notebook and Python.
But do you have any instructions of the software installation?
It's very simple.
Or any?
You can find it on the internet.
Well, for the environment configuration,
It's very simple.
Just
try first. If you don't understand, if you don't know, if you have any problem, talk with the GA.
All right. And for the detail of the software, we will upload it.
No, you have to find it yourself. It's very simple. It's just that. It's like a browser. It's like a Google Chrome or it's very simple thing. So it's nothing to explain there because you just find here, for example, Jupyter Notebook.
We just use this.
Have you tried Jupyter Notebook?
Have you used that before?
Yeah, so this one, right? Jupyter Notebook. Just that one. Okay. Installing Jupyter. Try Jupyter.
Okay, thank you.
All right, so let's start our second session. There were a few questions during the break, and I think the questions during the break were very, very useful, and I would like to share with you some of the questions. So the first question was, how how can we install Jupyter Notebook? So if you do not know, how many of you know about Jupyter Notebook or have used it before? Jupyter Notebook, how many of you have used it before? Okay, so only half of you here. So Jupyter Notebook is very simple kind of things. So my suggestion is just, search Jupyter Notebook, right? So that's what you search on Google. And then, there is a Jupyter Notebook, try Jupyter Notebook, installing Jupyter, and so on. Right? So it is a very simple and very, very popular actually. And Jupyter Notebook is a file, right? And what you have to submit for your CA, for your assignment, is the Jupyter Notebook file. The Jupyter Notebook file and the extension is IPYNB. That is the extension of Jupyter Notebook file, IPYNB. And that IPYNB is something that you have to send as your submission. And you don't just submit your code, but you have to compile and show the results on the notebook. So I have to see the results on the notebook. Okay, so you cannot just submit your source code. So that's the things about Jupyter Notebook, because in Jupyter Notebook, like I just show you, when I show you my code, it actually consists of the code and the results. So I don't need to compile because I will see the results there. And that's the result that you will get when you compile the Jupyter Notebook. Is that understandable? So you have to compile and run on the Jupyter Notebook file. And that's also in your submission. Yeah.
Combine just running all the cells?
Running all the cells and then send that to me. Okay, so you should be able to see your results on Jupyter Notebook. You cannot run your code on the other environment. You have to run it in the Jupyter Notebook. Yes. Yeah, a good question. So the code will be one of the things. Okay, the correctness of the code. So I will see the results first. If it's correct, then I don't really much care about the prettiness, the compactness, or whatever the code is, right? As long as it's correct, it's correct. That's one thing. Now, if it is not correct, then I have to do debugging. And then from the debugging, there will be the score for you. That's for the code. But in the CA, aside from the code, there are some questions as well. You are asked to do this, you are asked to do that, and then ask some discussion. So that portion of the discussion will be taken into account as well. The correctness of your answer and the preciseness of your answer. Okay, any other questions? So the thing is that if you are incomplete in your answer, there will be penalty. So I encourage you to write more, but if you write more and wrong, you also get penalty. Okay, so the correctness has to be the most important thing. The correctness and the completeness. Correctness and completeness. Anyway, so I will show you again the Jupyter Notebook thing so that you don't misunderstand what is the expectation. So this is what I said. Unfortunately, I cannot take everything in one page. So basically, this is the code, right? And if I compile this, when I compile, it's just shift enter. That's what I compile. And the result will be on the notebook. So this is called notebook. And this that you have to submit. This file that you have to submit. So if you look at the file there, the extension is IPYNB. Again, you cannot just submit your code. You have to submit your result as well. So this is the result here have to be submitted as well. If I don't see the results in your notebook, you will get deducted. Okay, so please show your result as well. So I can be sure that you have done correctly there. I mean, you have done the compilation by yourself. Okay, any questions on the on the submission or on the CA in general. Right, so if there's no questions, another interesting question was on the meaning of the prior. So I wrote P W bar equal to Gaussian of W bar 0 alpha I. Sometimes alpha or alpha inverse is just follow the textbook or follow the lecture note. Sometimes I use alpha inverse or sometimes I don't use the inverse. Anyway, so if it's inverse, then it has to be inverse for alpha, but it doesn't really matter because alpha is just variable. Anyway, so the question is, what is the meaning of this, right? First of all, you have to know the meaning of the multivariate Gaussian. So look at the internet for multivariate Gaussian. Multivariate Gaussian. So if I search here, for example, right, multivariate Gaussian. So I will have this Wikipedia, just click on Wikipedia. This is called also multivariate normal distribution, they're the same thing. So then you need to know this one, the function, where's the function? This one, PDF. Probability distribution function. So that is the probability distribution function, the definition of G that I wrote in the lecture note. So that is the determinant of 2 pi. Sigma is the covariance matrix. Power to half exponential function and so on. That's the definition of multivariate Gaussian. So in our case, it will be, let me see, if in our case, if I can write here, it will be, what is that? Determinant of 2 pi sigma. Sigma is alpha inverse I, the covariance of this, power to minus 1/2, exponential function of 1/2 x minus mu. In this case, mu is equal to 0. We don't care about 0 anyway. So in this case will be W transpose sigma. Sigma is alpha inverse I multiplied by W. So that's the operation that you have to apply. So that's the definition of multivariate Gaussian. Okay. Fortunately for us, this one is a simple operation. So in this case, you can just simplify it into exponential function 1/2 alpha, right? W transpose W. Okay. Any questions on that? Right. So that's all. Meaning, what is the meaning of this? How can we draw, right? So let's assume that you have W bar. So let's assume W bar equal to W1 and W2, means that we only have two Ws. So in that case, if this W is equal to scalar, or like in the case of univariate Gaussian, then that's what you have. Sigma square is actually this one, sigma standard deviation. This is for univariate Gaussian. For multivariate Gaussian, then you have to have multiple dimensionality. And in this case, because we assume only 2 dimensionality, W1 and W2, then you have W1 here and W2 there, and the z-axis will be the probability of W1 and W2. This one is actually the same as, this one equal to the same as PW bar. Okay? So the Gaussian will look like this in multivariate Gaussian. It's 2 dimensionality. Okay? And what does it mean by a covariance in this case? the covariance is this one here, alpha inverse in this direction and alpha inverse in that direction. Okay, that's the standard deviation in one axis. But now we have the covariance, our covariance in this case, our covariance matrix equals to alpha inverse I, right? And in this case, if it is two-dimensionality, then sigma, the covariance matrix is 2 by 2, and this one is 2 by 2. And in this case, it's very simple, right? You can just assume this one is, you can have this alpha inverse 1, 0, 0, 1. That's the definition of identity matrix. And in the end, you will end up with alpha inverse 0, 0, alpha inverse. And this one, as I mentioned again, is a square. It has to be square. And also symmetric matrix. If you don't know symmetric matrix, it doesn't really matter. It's okay. Right? But this is have to be symmetric matrix. Okay, any questions here? Yes.
So the alpha here is precision or variance?
Alpha inverse is yeah, good question. I do not know. It must be precision because it's inverse.
So alpha inverse actually
Precision is the same as beta. Yeah, but it doesn't really matter because you know they mathematically they're the same thing anyway. It's just the term. Yeah. Okay, any questions for this one? Again, for W bar, you have to imagine this one is multidimensionality. Yeah.
I think you're not recording the screen.
Oh, really? Yeah. I see. Yeah, you're right. I didn't. So sorry for that. Yeah, this technical thing is always bothering me because I have to. It's a bit complicated. When did this happen? Oh, no.
I think it's after the break.
Hopefully after the break, yes. Okay, yeah, hopefully after the break or after I plug out this dongle here. But anyway, so yeah, remind me, please help me to remind that the recording have to be there and the screen have to be shared. Anyway, so okay, any other questions here? Okay, so let's discuss about basis function. So the motivation is clear that you know I show you that if you use polynomial function, the problem is that it's very difficult to control because the power is very, very large. And if the power of this x, normally if x is greater than 1, power of something that is very large, it will be very, very large, right? That's for x. So remember that you have this polynomial function, yn. So you have yn equals to w0 xn0 plus w1 xn1 plus xn power to I plus wm xn power to m. So this is polynomial function. So this is polynomial function. Right. So So as I mentioned again, it's likely that x, the value of x is greater than 1. For example, for here, the time is greater than 1. So if your m is 1,000, for example, make it extreme, then it is power to 1,000, which is very, very huge, right? So if it is very huge, if this term is very huge, what happened? And the underlying function is actually much simpler. So m truth, the truth of m is very simple, for example, 3. So in that case, there are many w that have to be encouraged to be 0, right? So in that case, this one is inevitably large. And this one have to be inevitably to be very low, because likely that they have to be cancelled. So you're dealing with very, very large number in one end and very, very small number in the other end. And this causes instability because there is a limit of numbers that you can capture by your computer. Right? So there's a problem there. Another problem is that for every pixels, you have to deal with all this big equation. For every sample, you have to deal with all this big equation. In other words, this big equation, this polynomial function, have to be applied equally to all samples. And it is somehow called global function, right? And that is the problem as well. If it is global function, it's very difficult for us to pull it here and there. So that's why I show you in the example that I gave to you, even though it's 150, for example, it's not really like the expectation will be something like this. That will be ideal kind of overfitting. But instead of that, the polynomial function only gives you somewhere like that. It's not flexible enough. It's very rigid because it's a global function. And that's the difference that we want to make. The blue one is a polynomial function. The blue one is polynomial function. The red one is basis function. General basis function. Well, polynomial function is part of basis function actually, but basis function there are many different basis functions that can be made locally. So this one is actually local, can be a local function. Different location will have a slightly different function. So I will discuss further later on what it means by local function. And this local function makes the flexibility of the curve much, much improved. Any questions so far? Okay, so that's the intuition behind this. So let's get into the details of the mathematics of Gaussian function. Okay, so again, if it is polynomial function, we have yn equals to sum over m wm xn power to n equals to w transpose xn bar. If it is general basis function, then we have yn equals to w0 plus m equals to 1 until m minus 1, which is actually the same as polynomial function. But the difference here is that wm have a function phi of xn, phi m of xn. So this is the difference basically between polynomial function and basis function. But again, basis function can capture for polynomial function as well. So that's the difference in between box. And now what is phi here, right? What is phi m? Well, phi m here has a name first of all. First of all, this one is called basis function. So in polynomial function, for polynomial function, phi m xn equals to what? Anyone? X n power 2 m. That in that case, the basis function is actually exactly the same as polynomial function. And what we use to make it flexible is not polynomial function, of course, but we will use Gaussian, one of them, Gaussian basis function. And if you use Gaussian basis function, then the definition of phi m xn equals to exponential function of minus xn minus mu m squared divided by 2s squared. So there is a hyperparameters. The hyperparameters are mu m and s squared. Any questions here? I can use many other basis function, but for now, let's learn about Gaussian basis function first. All right, any questions here so far? Yes. Yes, this is a radial basis function, basically, yes. Yeah, that's true. This is called, another name of this is radial basis function because this is based on radial function, which is in this case a Gaussian function.
We will have the mu as a vector.
Mu, that's right. Mu can be a vector. That's a good question. I forgot to mention this. So now, if you look at the polynomial function, right? Here, the polynomial function for xn bar equals to xn 0, xn 1 until xn m minus 1. Right? That's the definition of xn. In this case, what is the dimensionality of your data? What is the dimensionality of xn? Xn itself, what is the dimensionality of xn?
And 1 by 1.
1 by 1. That's right. It is one dimensionality of data. In this case, time. Time is just one dimension. So now, of course, we're not dealing with time all the time. We can deal with many different data. And in that case, xn is not necessarily just one dimension. It can be 2 dimensions, it can be 3 dimensions, it can be 4 dimensions. So if it is 2 dimensions, how can I write this in polynomial function? How can I write this? So forget about this one. So I can write in the factor form something like this, right? So it itself here is multiple dimensionality. But then how I can write this part? This one is become what? Become a matrix. If it is 2 dimension, it becomes a matrix. But if it is 3 dimension, it becomes what? It becomes a tensor, 3-dimensional tensor. If it is 4 dimensional, it becomes 4-dimensional tensors. So this one becomes complicated, right? Writing this one is complicated. So that's the problem. Another problem with polynomial function. If your data, in the nature of your data is very high dimensionality, the writing of this equation becomes very awkward. Well, it's doable mathematically, but it's very difficult in terms of the derivation and so on, because it becomes tensors, right? So, and that's a good thing about polynomial basis or Gaussian basis function. We will see later on, we have a freedom to make xn multiple dimensionality. Why is that? Because here is the case. I can just give you an overview here, but there's a interesting meaning behind that actually. But anyway, so in this case, it's 1 by 1. Right? If it is 1 by 1, the polynomial function can do the job as well. But if it is 2 by 1, for example, or d by 1, d is the dimensionality of your data, right? then you can transform this one into multivariate Gaussian. This one become multivariate Gaussian. At the moment, it's just univariate because X is assumed to be 1 by 1, but it can be multivariate Gaussian. And if it's multivariate Gaussian, it's become covariance. That one become a vector, and S become covariance. But in any way, that's the power of basis function as well. Although this one is d by 1, after the transformation, after the Gaussian function here, the output, what is the output of Gaussian? Is a matrix, or it is a vector, or it is a scalar? It's a scalar. The output of your Gaussian is always scalar, right? So this one in sigma here is always 1 by 1. So that's the power of the mathematical power of Gaussian basis function, because your data can be in any dimension. But after the basis function transformation, it becomes 1 by 1. So in that case, it can be always valid. Although you have multiple dimensionality, in the end, by the transformation of phi, it becomes 1 by 1. Is it clear? Any question on that? Okay, anyway, so we will see later on why this is powerful, why that transformation for high dimensionality into 1 by 1 is powerful. We will learn later. Okay, anyway, any other questions here for phi? Okay, so now how we can do the operation, right? So first of all, what is the intuition of this? The intuition of this, one of the, I'm not really sure how many of you know PCA. How many of you know PCA? We will discuss this in the second session of the course, of course. But PCA, you know, how many of you know about principal components? You know, the first principal components, second principal components, eigenvectors, eigenvalue. How many of you? Ooh, okay. So I cannot use this as an example. Okay, so let's take a look at a very, very basic example. How many of you ever play Lego blocks? Lego blocks, anyone? Yeah, Lego blocks that you learn when you're a kid, right? I think everyone here knows about Lego blocks. So Lego blocks, the blocks is a very simple shape. The block itself can be very simple shape. But when you combine them, you can have a very, very complex shape. So that's called basis function. Basis function is the building blocks of your component. So that's the very intuitive example that I can give to you. Now, in mathematics, what kind of function is similar to Lego block? You can have any function from very simple functions. What kind of example? Again, you can have very, very complex function, but you can decompose this complex function into very simple functions. Yes, sine function. What is it called? What kind of transformation is that? It's called Fourier transform. Fourier transform is only depends on sine and cosine. Sine and cosine is very simple function, but you can create very, very, very complex function only based on sine and cosine. And it was invented by a guy called Fourier, right? And it is 400 years ago. So it's not a recent invention, it's 400, 300 years ago. And that's the idea here. We want to use a very simple function, in this case Gaussian function, to create a very complex function. Okay, so that's the basic idea of basis function. So how can we get into this very complex function? What is the operation that we have to do here? Yeah, so I give a very simple examples on the lecture note, but I don't want to go through every details on the lecture note because I think it will take time. So I just give you the intuition behind. Let me see. Okay. So imagine you have one sample of data. Okay, so one simple sample, just one sample of data here. And again, this one is for the simple case, this is xn, year or time, and this is yn or tn, which is the price. And if you want to model this using basis function, then you can use, for example, m here. For this one, you consider this function here, right? The blue function there. So you have to consider m equals to 2, for example. So in this case, where m equal to 2, then you have w0 plus, so if you have m equal to 2, you have yn equal to w0 plus w1 phi 1 xn, correct? You only have one support of phi. So this one, phi here, is a Gaussian function. It means what? It means that you will have a Gaussian function there, maybe not like that, maybe something like this, not that far from the point. So this one is your point. And this one here is what? What is the value here? Anyone? What is the value of the blue dots? Is mu n. Yeah, in this case, mu1. And we want to fit the function of the line here. If it is a line, because m equal to 2 is a line, right? It's a line there. We want to form that red line based on this blue function or blue curve. Okay, so we want to use a blue curve to form a line. So that's the basic idea. And whether or not we can get the red line from the blue line, I'm not really sure. Maybe we can, but you know, if your model is, well, I will explain later on. Let's look at the mechanism first. So basically, we try to get this one. We know the function here is basically this one, right? So we have to find W0 and W1 that use this blue line, you can get the red line. That's the basic idea. So you have to find W0 and W1 in such a way the blue line become the red line. Of course, in this case, it's not possible because you only have one point, one sample. And as we know that it will be too many possibility of that. So it's not possible. But assume that if you have 2 points, and you can use this function to find W0 and W1. Okay, so that's the basic idea of this basis function. It's not really intuitive. I understand that it's not intuitive. It's very difficult for me also to explain to you. But magically it works. Because if it is 2, m equal to 3, for example, m equal to 3 means that you have 2 Gaussians. So now you are supported by 2 Gaussian. Then you can draw the red line even better. Okay. So basically, you have to try. You have to do the coding here, and then you will see the power of this basis function. If you learn about Bayesian spline or B-spline, how many of you know about B-spline or Bayesian line. Yeah, if you're not computer scientist, you will not learning about this. But anyway, this is the basic the concept of that one is the same. So I can give you the basic idea of B-spline or Bayesian spline. So basically, this is the same. We can have many different curves like that. For example, from a few dots. So the dot is the point given to you, and then you can get this line very complex based on Gaussian function, or in this case, B-spline as well. Right. So this is the basis function. So many Gaussian, and based on this Gaussian, you can create a very complex line. Okay, so there are basis function here, and based on this, you can have a very complex line. Anyway, so that's the intuition behind. It's not intuitive, I understand, but if you code it, if you program the equation, you code the equation on your Python, for example, you will get the intuition. All right. So I can show you quickly on this. Right. Okay. So I will show you a bit on this. So this is the shape here is because of the basis function, and the basis function that I use. So this one is I use a Gaussian basis function, and I start u from 0. So because there are multiple u, if you have m equal to 100, for example, then you have u or mu 100 values. So in this case, I start from 0 and I increment the value of mu based on my s. That's how I have the value of my mu. Okay. Now that one, so you can imagine that it will be, I will explain this later on, what is the effect of this. But basically you can assume that the Gaussian is the support for your points, support for your line in that point. Okay. So that's the idea here. We have, in this case, we have to define m, and m here is 3 or any values that you want. Right. So okay. So m here is 150 in this case for this MEP, and you can imagine there will be 150 basis function along this line here. So, but anyway, so my suggestion is that do the implementation, so then you will know what it means. So basically, we have parameters called mu here. So we have parameters of mu1 and mu2. And mu1 and mu2 cannot be far away from your dots or your samples. So for example, if you have your dots here, for example, and you define your mu far away from this, there would be no support for your samples because the function that we use, although Gaussian is infinite, so Gaussian is very something like this. And if you have 2, for example, the most expressive part of this is here. That's the most expressive part. This one is not expressive because it's just a almost horizontal line, right? So if we support this one with that almost horizontal line, then it will be underfitting. So your mu cannot be far away from your points. So in this case, you have to define your mu here. Okay, so that's the rule. You have to set your mu correctly, not far away from your points, because that's the support system that you want to give to your local pixels, in this case, local points, I mean, local samples. Okay. So another good thing about this basis function is local. Local means that if you have a data point, something like, very dense in one part and very sparse in the middle and very dense in the other part, for example. So this one here in the middle is empty. So in this case, you know that it's empty because there's no data. So in that case, you do not need to put your Gaussian function. You don't set your mu in that location. You can set your mu nearby the location that have data. So this is what we call local. Okay, so you can set your mu wherever you want to support your data. And this is done locally. So in this local operation, it can be really overfit. So that's the advantage of basis function. Any questions here? Okay. Anyway, so you have to experience with the coding, with the code, and then you can get the intuitions. Yes.
So the points would be supported by the government.
Yeah.
Distribution, not only the peak value, right?
Not
only the peak value, which is the mu. It will go around.
Yeah. So all this shape. So as I mentioned again, that's a good point there. So all this location here is very expressive. You have vertical line, you have somehow like curved line, and so on. And that is used to form your function, the red line function, this red line function here. And if you only have this one here, it's not expressive. Because in that point, for example, in that location here, the support system is not that much. But if you have more basis function, so for example, more basis function means that, for example, for this point here, if you have something blue there, it is some of this and some of that. So you have two support function for that particular point. Okay, yeah. So, for example, if you are unfortunate and actually there is a data in the middle, but you do not know this data and you do not set any mu in the area, then the line here will be underfitting, will be underperformed, because there is no support system for that one. Well, there is a support system, but it's very not expressive because it's just a flat line, flat curves.
Are we trying to minimize the number of Gaussian?
Well, that depends. The number of m here is something that you have to set. The complexity of the model is based on the number of your curve, which is the number of curve is m basically. Now, in polynomial function, you don't really care where the function is. You just set m and that's it. But in basis function, the disadvantage is that you have to know where you have to put your basis function. You're not only knowing m, not only setting m, but knowing where they are, right? If you do not know, you can put it uniform, of course. Any questions here? Okay, so if there's no questions, that's all for basis function. In the textbook, actually, there's some explanation, discussion in one section, I think, and you can read further on that. Yeah. So mu is something that you have to define. So this mu here, this mu1, mu2 until mu m is something that you have to define. In my code, I'm trying to make it automatic. I set mu0, mu1 as 0 from 0. Increase this incrementally with certain parameter s, which is the standard deviation. In that case, I don't really care where the location of the basis function. I just make it uniform. Right?
We are only optimizing the W.
So we are optimizing W. Yes, we don't really minimize optimizing M and mu. We haven't get into that point yet. So you have to define mu as a hyperparameters that you have to set. The same as you have to set M that you have to set by yourself. Okay. Any questions?
If you set the mu's uniformly,
Yeah.
you will have a support for the
all area.
But
Yeah.
will that make the model underfitting?
If your M is high, it doesn't really matter, right? Because you will have many support system anyway, support bases anyway. If your M is very high, and that's something that you need to set, right? If you do not know M, just set it high. The prior will take care of it.
But all the M's will have the same standard deviation, right?
If you don't want that, you can modify S to be different from different basis function. But that will create another problem of how we set the standard deviations. So in many cases, if you don't want to set this in complex way, then you can set it uniform.
But if we set it uniformly across all the
Yeah.
functions and the mu distributed uniformly,
yeah,
it's difficult to represent any curve because it will be straight lines.
No, it still can be complex function. You don't need to worry about that. The complexity of the function is based on how many basis function you have at that part, at that region.
But at each region,
if it is uniform, then it doesn't limit. S is not that important. S is not that important. The most important thing is the uniformity of the standard deviation. The thing is that if S is small, right? If S is small, your M, for example, I can give you the example of the problem if S is small. So if I use mu I equals to mu I minus 1 plus S. For example, if I use this formulation to automatize the value of mu I, so then I don't really care much about mu I, the location, right? In this case, if your S is large, it will be large, it will be sparse. But if it is F is small, then you will have something like this. Which one is easily overfit? Which one? 1 or 2, which will be easily overfit? 2 is easily overfit because in that particular location is very complex. The complexity of the model now is very complex here. The complexity of your model is very simple there. So number 1 is possibly become underfitting. Number 2 is possibly becomes overfitting. But you don't care about overfitting, again, because the prior in MAP will take care of your overfitting problem. Okay? Just be careful with this, because if your data is here, for example, and you set M equal to 5, and S is to very small, for example, then this 5 of basis will only occupy the region. There's no support for the region. It means that it will be overfit here, but underfit here.
You have to make sure that mu will cover the standard.
That's right. That's what I said, that you have to make sure that it's covering all the regions of the place that you have the data. Yes.
So initially our polynomial questions, right? We are trying to look, the input is the coordinate of the points. Then we have this output of the rate. But now you're introducing the basis functions, which means actually we need to, the input itself is the Gaussian.
No, the input is the same. So look at this one again. Look at this equation here. All right. The basis function, if it is polynomial function, is that one. That will be polynomial function. Now you change that into that one. That will be a Gaussian basis function. There's no difference actually. The input is still xn. The output is still w. There is no change at all. Of course, you have changed to this one. You have to define that one. But once we define these two parameters, hyperparameters, They are exactly the same in terms of the mathematical operation. There is no change in the mathematical operation.
Actually, that's my question. Now that the mu inside the basis function, right?
There's mu and s, yes.
The mu and s itself will change the value.
No, we don't treat them as random variable. We don't treat them as random variable. What we treat as a random variable is still w. This one is called hyperparameters. Hyperparameters means like m. You have to set it before running the code. So you assume that mu and s are already given to you. If it's given to you, it doesn't really matter, right? It's the same as the basis function now. Okay. Any other questions? Yeah, that's one of the questions. Any other questions? Right. So if there is no further questions, my suggestion is that look at the lecture note. There are some examples there that make you easy to understand, and try to write your code based on the equations. Actually, this is part of the assignment anyway, so you have to do it. Okay. All right. So now we assume that we done with the basis function. Okay. So because everything there is actually the same as polynomial function. But anyway, so let's look at the example of how we use a basis function. Let me see. Okay, so MLE, basis function. We've done this a few times already, so I think you know MLE. So in the first step, we want to have modeling, data modeling. So in polynomial, Yn, or probability of likelihood of Tn given Yn is x bar w, sorry, not x bar in this case, xn w bar and sigma square. I can use let me see. Okay, so anyway, so that's fine. This one is a Gaussian function of, anyone remember? Input, what is the input? Tn. What is the mean? Yn. What is the division of Yn in the polynomial function? W transpose x bar n, right? What is the standard deviation? Sigma square. That's if you use polynomial function. Now, if you use basis function, let's have a different color. Then this one equals to Gaussian of Tn. What is Yn then? W transpose phi xn. That's it. Everything is the same. So what is a phi bar here? What is phi bar xn? Equals to, this one is vector, right? When it is bar, it's always a vector. So what is the first element here? Phi 0, right? Input xn. And the next one, phi 1 xn. Until phi m minus 1 xn. Now, what is phi 0 xn equals to what? No, equals, if you look at this, what is x z, what is phi 0? What is phi 0? 1. That's right. Phi 0 is 1. So you have to be careful with this. This is in your implementation. You have to remember that phi 0 is actually 1. And phi I, or any 1 or 2 or 3 is fine, equals to, then 1 is the exponential function of minus xn minus mu I, right? Square divided by 2s square. Any questions so far here? Yeah.
The code. So the m in the code isn't the same as the m here, because I think there you can put it as 0, but here you cannot.
Yeah, so basically they are the same thing. So the equation using basis function become yn equals to w0 plus sigma m equals to 1 until m minus 1. So this one is m equal to 1 of w m phi m xn. Actually, they are the same thing. So in this case, if you want to, if you know that phi 0 equals to 1, you can just sum over m equals to 0, m minus 1, wm phi m xn. It's the same thing. But you know that phi 0 equals to 1. You have to know that phi 0 equals to 1. Okay. Any other questions? And the rest is exactly the same. It doesn't really matter whether this is the difference is only here, right? The difference is only there. So that's the difference here in the green area there. And mathematically, they are the same thing. So the operation by the derivation of the equation are all the same. But the consequence of this, if you look at the lecture note later on at home, is that W bar star equals to, if it is polynomial function, so if this polynomial function is polynomial, then W bar equals to, anyone remember? If it is MLE, what is W bar? X transpose X inverse multiplied by X transpose multiplied by T bar. Right? Now, if this basis function, W bar equals to what? This one is phi transpose phi inverse phi transpose T bar. So what is phi there? Phi is a matrix, of course. And inside this matrix, is the same as the dimensionality of this phi is what? Anyone remember what is the dimension of phi? N by m, yes, n by m. So in that case, because it's n by m, the row indicate your samples. Yeah. So the row indicate your samples means that you have phi 0 x. Well, we start with x1, right? x1 phi 0 x2 phi whatever this one just dot 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 phi 0 x n. And then the next here is phi 1 x1 dot 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 phi m minus 1 actually minus 1 x1. So this is something that you have to be careful in your coding because you will use this in your implementation. Phi, anyone? M minus 1 of x and yeah, so that's the things. So everything here is 1. But the rest, you have to compute using Gaussian exponential function, using Gaussian basis function. Any questions? Okay, so if there is no questions, actually that's all for basis function. Let's move on to the next subject, which is Gaussian distribution. We have about 15 minutes. How many of you want to continue? So how many of you want to go home? Yeah, let's go home. All right, thank you, everyone. I will see you next week. Thank you.
Professor, you said that the mu is set by us.
Yep.
But the IMA is
So you can
we obtain IM from the
So mu m, you can set it as a mu m minus 1 plus s. You can define in that way. So in this case, you don't really need to define mu. So mu 0 can be 0.
Okay, so
But you need to s. So s is the, for example, 0.1.
but before the program on, we don't know how what the IMA is combined M.
Yeah, you have to set m in any case, right? M have to be set. Even in polynomial function, you have to set m. But you don't need to worry because as we discussed, you can set m as high as you want.
Okay. And the IMA is set by itself.
You have to set yourself, yes. But MAP will take care of the overfitting problem. So you don't need to worry about the
So
high.
if IMA is too high, it doesn't matter.
For MAP, it's okay. But
Oh,
for
okay.
MLE, it will be overfitting.
Okay, I got it.
Right, Paul. Just a quick question. We took the MLE and MAP. What happened to full Python? You said that we
That's one. I want to discuss about Gaussian distribution before getting into
I was
Bayesian.
getting confused. I thought that we skipped it.
No.
Thank you so much.
Yeah, no.
Are we going to release the assignment?
Yeah, tomorrow, I think. Yeah.
Thank you so much.
For the visual computing, I don't see any notes and it's not fully uploaded.
This one is visual computing, right?
Visual computing.
Yeah.
The written notes and this one, I think something is missing to upload.
Oh, can you click this? You can download this one, right?
Oh yes, I can.
Oh, what you mean is the previous one?
Lecture one.
Lecture one that is actually in the lecture 2. It's here.
Oh, everything is here.
Yeah. So this one is already there.
So it's combined.
It's combined in lecture 2. Yes. No, it's.
Hi.
Yeah.
Can I ask you for the MEP, right?
Yeah.
You changed this initial, what do you call it, the posterior into
the posterior into likelihood and fire.
So because the yn can be expressed as w bar times xn, so you take out the xn from the right side.
Yeah, I combined that into yn. So the posterior is a p posterior, right? Yn given pn. Actually, this one have coming from w trans w bar and sigma tn xn. So this is the correct writing.
Right.
But we know that yn equals function of w bar and xn. And xn is given to you, is known. Right? So now that's what I said, that w and yn become twins. They can represent, they can swap each other.
Right.
So that's why I swapped this one with yn.
Right.
And in that case, because xn is a of yn, I don't really write yn here because yn is already here.
Okay, right. I understand. So from then onwards, the next part you express the the
using
PDF as the using the base theorem.
yeah.
Okay, then after you said you can split this P Yn due to independence.
Yeah. So if I
you assume
P,
that Yn and sigma they are independent.
Yn and sigma. Yeah. So this one is actually P x and W bar and sigma square, right?
Okay. Yeah. Then in the end, you said the P sigma square you can change it into 1.
Yeah. So this
why
one I split x and W bar with this one means that they're independent, right?
Yeah. Yeah.
So and then this one, of course, if you happen to know the function of this probability, you have to use that function.
Right.
But in this case, we do not know what is the prior of for sigma square.
No, but this the okay.
This is the sigma square is the noise.
Okay.
So if you know the prior of the noise, of course you can find that.
Right.
But normally we don't know the prior of the noise.
Okay. So you don't know, then you just put it as 1.
Yeah, you just put it as constant.
Okay.
Because in this case, that one become uniform. For every sigma square, it's uniform. So this means that there's no priority for certain value.
Okay.
If you know the probability, means that you give the priority to certain value here.
Okay, I see.
Right. That's when you know that you have where in sigma square that you have to set.
Okay. Then after you said the prior of xn can become a constant also.
Yeah. This one is if it is C here.
Right.
C, if C is there, this becomes C, right?
Yeah.
So you can replace this as with C.
Okay.
Right. So now why I set C equals to 1? Because in the end of the day, for MAP,
right,
we just use the max.
Yeah. Cause the differentiation will get rid of the constant.
Yeah, constant will be, it doesn't matter, right? Constant or 1 doesn't matter.
Yes, that's right. That's right.
Yeah.
Yeah. Okay. Yeah. Then the. Yeah, you split the pipe.
Yeah, this one I split further.
Yeah,
yeah, I split that further. If you know this one, if you know the correlation, it's fine. You have to use that.
Yeah.
But this one is for the discussion, for the sake of discussion today.
Okay.
We just assume a simple case when you can split.
Okay, then in the end you
I make this constant as well. So for the sake of the discussion, I put it as constant.
Okay, I see.
So the main point why I ignore this, because I just want to emphasize this. The main point is that this one is the most important part.
I see. Then you use that to solve the overfitting.
That's correct. Right? Yes, because our problem is overfitting, and that can be solved using this prior on W.
Okay, I see. Thank you very much.
No worries. Yeah.
Professor, I wonder, can I use MATLAB kernel in the Jupyter notebook?
No, you have to use Python.
I must use Python.
Yes.
Okay, thanks.
Yeah.
So I want to ask a question about the prior. You say that the alpha I is the covariance matrix.
Yes. So alpha inverse actually. Yes.
Alpha inverse.
Yeah.
So is this just the case when
sorry, I just want to stop the recording.
Okay.